Electrical engineering is a vast and dynamic field that forms the backbone of modern technology. From the electricity that powers our homes to the sophisticated circuits inside smartphones, electrical engineering touches nearly every aspect of our daily lives. For beginners, understanding the basics of this discipline not only opens up a world of innovation, but also lays the foundation for more advanced studies and practical applications. To embark on this journey, it is essential to grasp the core concepts, fundamental laws, and key components that define electrical engineering. At its heart, electrical engineering deals with the study and application of electricity, electronics, and electromagnetism. The field encompasses a wide range of topics, but it all starts with the basic building blocks: voltage, current, and resistance. Voltage, often described as electric potential difference, is analogous to the pressure that pushes electric charges through a conductor. It is measured in volts, V. Current, E, measured in amperes, A, refers to the flow of electric charge, much like the flow of water through a pipe. Resistance, measured in ohms, O, COS, is the opposition to the flow of current, akin to friction in a mechanical system. Understanding the interplay between these three quantities is crucial, and their relationship is elegantly captured by Ohm's law. Ohm's law states that the current flowing through a conductor between 2 points is directly proportional to the voltage across the 2 points and inversely proportional to the resistance between them. Mathematically, it is expressed as I equals V R, where I is the current, V is the voltage, and R is the resistance. This simple yet powerful equation is the cornerstone of circuit analysis and design. By manipulating this relationship, engineers can predict how much current will flow in a circuit when a certain voltage is applied, or determine the necessary resistance to achieve a desired current. Moving beyond individual components, electrical engineering often involves working with circuits, networks of interconnected electrical elements. Circuits can be as simple as a single battery connected to a light bulb, or as complex as the integrated circuits found in computers. There are two main types of circuits: series and parallel. In a series circuit, components are connected end-to-end, so the same current flows through each component. In parallel circuits, components are connected across the same voltage source, so the voltage across each branch is the same, but the current divides among the branches. Understanding how to analyze and design these basic circuits is a fundamental skill for any aspiring electrical engineer. Another key concept in electrical engineering is power, which is the rate at which electrical energy is transferred by an electric circuit. Power is measured in watts, W, and is calculated as the product of voltage and current, P equals Zix. Efficient power management is critical in everything from household appliances to industrial machinery and renewable energy systems. Engineers must design systems that deliver sufficient power while minimizing losses due to resistance and other factors. As one delves deeper into electrical engineering, the role of passive and active components becomes apparent. Passive components, such as resistors, capacitors, and inductors, do not amplify or generate energy. They simply store or dissipate it. Resistors limit current, capacitors store electrical energy in an electric field, and inductors store energy in a magnetic field. Each has unique properties that influence circuit behavior. Active components, on the other hand, include devices like transistors and operational amplifiers. These components can amplify signals or switch currents on and off, making them indispensable in modern electronics. The study of alternating current, AC, and direct current, DC, is another foundational topic. DC refers to the unidirectional flow of current, typical of batteries, while AC refers to current that periodically reverses direction, as in household power supplies. AC is widely used for power distribution because it can be easily transformed to different voltages using transformers, enabling efficient transmission over long distances. Understanding the differences between AC and DC and the appropriate applications for each is vital for both safety and efficiency in electrical systems. Electromagnetism is a central pillar of electrical engineering, underlying the operation of motors, generators, transformers, and many other devices. When an electric current flows through a wire, it generates a magnetic field, and conversely, a changing magnetic field can induce a current in a conductor. These principles, first described by scientists like Faraday and Maxwell, are harnessed in countless applications, from producing electricity in power plants to enabling wireless communication. Measurement and instrumentation are also crucial aspects of the field. Accurate measurement of voltage, current, resistance, and other parameters is essential for designing, testing, and troubleshooting electrical systems. Tools such as multimeters, oscilloscopes, and signal generators allow engineers to visualize and quantify electrical phenomena, ensuring that systems operate as intended and meet safety standards. Safety is paramount in electrical engineering, given the potential hazards associated with electricity. Even low voltages can be dangerous under certain conditions, and high-voltage systems require strict precautions. Proper insulation, grounding, circuit protection devices like fuses and circuit breakers, and adherence to codes and standards are all essential practices. Beginners should develop a healthy respect for electricity and make safety a habit from the outset. Digital electronics represents another major area within electrical engineering. While analog circuits deal with continuous signals, digital circuits process discrete signals, typically represented as binary values, zeros and ones. Digital logic forms the basis of computers, microcontrollers, and many communication systems. Learning about logic gates, flip-flops, and microprocessors introduces beginners to the world of computing and automation, highlighting the close ties between electrical engineering and computer science. Communication systems, which enable the transmission of information over distances, are also integral to electrical engineering. From radio and television to the internet and mobile phones, these systems rely on the manipulation of electrical signals. Modulation, coding, and signal processing are key techniques that allow information to be transmitted accurately and efficiently, even in the presence of noise and interference. Control systems are yet another important domain. These systems use feedback to regulate the behavior of machines and processes, ensuring stability and desired performance. Whether it's maintaining the temperature in a room, controlling the speed of a motor, or stabilizing an aircraft, control theory provides the mathematical tools to design robust and responsive systems. As technology evolves, new areas continue to emerge within electrical engineering. Renewable energy, for example, leverages solar panels, wind turbines, and energy storage systems to produce and manage clean electricity. Power electronics focuses on converting and controlling electrical power efficiently, facilitating applications such as electric vehicles and smart grids. Embedded systems combine hardware and software to create intelligent devices, from medical instruments to home automation products. The path to mastering electrical engineering begins with curiosity and a willingness to experiment. Hands-on experience is invaluable. Building simple circuits, tinkering with breadboards, and using simulation software help solidify theoretical concepts. Many beginners benefit from kits and online resources that guide them through practical projects, gradually building confidence and competence. Mathematics plays a significant role in electrical engineering, providing the language and tools needed to analyze and design systems. Algebra, trigonometry, and calculus are frequently used to solve circuit equations, analyze waveforms, and model dynamic systems. While the math can seem daunting at first, it becomes more intuitive with practice and application. Collaboration and communication are also vital skills for electrical engineers. Projects often require teamwork, interdisciplinary knowledge, and clear documentation. Whether working on a small prototype or a large infrastructure project, the ability to convey ideas, interpret technical diagrams, and troubleshoot collaboratively is indispensable. The journey into electrical engineering is both challenging and rewarding. The field offers endless opportunities for creativity, problem-solving, and making a tangible impact on the world. From lighting up a room to powering entire cities, electrical engineers shape the future with every innovation. For beginners, the most important step is to build a strong foundation in the basics. Mastering concepts like voltage, current, resistance, and power provides the groundwork for tackling more complex topics. Engaging with practical projects, seeking mentorship, and staying curious about how things work will accelerate learning and open doors to exciting possibilities. As technology continues to advance, the demand for skilled electrical engineers remains high. promising a bright and electrifying future for those who choose to pursue this dynamic field.